relationship between potential and electric field. Very simple relationship I will give, and then I will go for the next task. See, we know very well electric field is equals to kq by r square. This is the magnitude of electric field. See, if it is in the vector form, it is different one, but I am taking only magnitude. So in the case of V, potential is nothing but kq by r square naught. What is the relationship? Easily we can understand. 1 by 2 we can do. So E by V is equals to kq cancel. What happens here? Kq by r square divided by kq by r square divided by, tell me, kq by r. kq cancel, r square will be cancelled. Now it is nothing but what you will be getting, tell me ma. E by r is equals to, what you will be getting? So E is equals to V by r. So 1 by r you will be getting. So if I class multiply this, then definitely 1 by r. It is 1 by r. You do the division process, definitely you can understand. So E is equals to, or else V is equals to E into R you will be getting. See, clearly it has given, this is R is a vector quantity here, it is a radial vector. E is a electric field, it is also vector. V is a scalar. What is this? A scalar. What is this? Vector. What is that? Vector. If two vectors are multiplied, if you are getting scalar, means it is definitely dot product. See, this vector concept will never leave you alone. So it will come, it will repeatedly it will be coming in every topic. Try to understand. See, potential is equals to the dot product of R bar and E bar. Or else magnitude of potential, sorry, it is not vector form. If you want to find magnitude of potential, means E R cos theta you will be writing. Where theta is angle between E bar and R bar. I hope you understand this topic. This is what relationship between E bar and R bar. See, potential is equals to E bar dot R bar. That's it. Flux is equal to E bar dot dA bar. Did you remember? What is that? Flux is equals to E bar dot dA bar. Did you remember? A bar. Anything. The same way, potential is equals to E bar dot R bar. Radial vector, it is areal vector. It is area, it is radius. Radius means distance. Are you understanding this point? Getting my point? Shall we go for the next thing? Yes, write down. Next thing what we are going to do. See, shall I rub it? Yes. If it is a point charge, definitely you will be able to find the potential very easily, as I told you. Okay, fine. See here, if it is Q, source charge is a point charge. I want to find V here, then what is the formula? EC, that is what? KQ by, let me consider A. So VA is equals to, this is a point A. I want to find a VA. VA is equals to KQ by, let me consider the distance between here to here is X, KQ by X. That's it. Suppose if it is not a point charge, a distributed charge, let me consider uniformly, shall I rub it? Uniformly distributed ring. You can consider the ring. I am considering the ring. Potential due to, write down, potential due to a ring of uniformly distribution of charge. Fine. See, a positive charge is distributed uniformly in the ring. This is what ring. Okay, fine, ring it is. Ring means inside, there is no matter. So this is the center O. Okay, fine. So I want to find the, let us draw clearly so that you can understand easily. This is what ring, so that you can understand easily. So uniformly distributed positive charge I am going to take here. This is the center of the ring. Let me consider axial point it is. Here the point is P. At point P we have to find the potential due to this ring. Potential due to a ring of uniformly distributed charge. How to find it? Shall we go with this? Yes, clearly. Let me consider a small charge I am going to take dq. So what is the distance between here and here? This 3-dimensional. It is ring is like this. From the center we have. Try to understand. 3-dimensionally you should understand. That's why ring I have drawn like this. 3-dimensional figure it is. This is the center of the ring. Let me consider the radius of the ring is r. The distance between here to here is x. Let me consider. This is the point. Then it will be square root of x square plus r square. Now, see what is the potential formula? Potential formula Vp is equals to, what is the potential formula? Kq by r, x square plus r square. Are you understanding? Are you getting my point? This is what Kq. So see, this is what K. Actually for small dq means dq you should consider. I mean dv. In this way we have to understand. dv. If you are writing dv here, dq you should write here. Try to understand. Try to understand the concept. So you know dv, both sides you can integrate this. Integration of dv is equals to integration of k dq divided by, this is square root, I am sorry, this is square root, x square plus r square. So this is constant, this is all constant, take it out. This is the integration of dv is v only. V is equals to k by x square plus r square into integration of dq means capital Q. So finally you will be getting the answer kq divided by x square plus r square. Very very important formula for the ring. Try to understand. Uniformly distributed ring, if you are considering here, means you should consider like this. I hope you are understanding this point. Yes or no? Are you getting my point or not? Yes or no? Next we will go for the one more derivation of this concept. So a bit, make a note of it. Potential due to uniform distributed ring. Now next very important topic, potential due to dipole. Potential due to dipole. This point, this is the topic. Next we will go for the other one. Potential due to a dipole. So far we have discussed electric field due to dipole. How many situations we have discussed? 3 situations we have discussed. What are there? Axial, equatorial, and then any point. Did you remember them? So these are the 3 situations we have discussed electric field, finding of electric field in the case of electric field. Now we are discussing in the case of potential. Okay, fine. Let me consider first potential due to a dipole. This is what the title. In this, the first case A is potential on axial line of the dipole. This is the first part we need to discuss. So let me consider there is a dipole, positive charge, negative charge. This is the center, you know, this is equatorial line. The distance between here to here is A, the distance between here to here is A. Let me draw an axial line and take a point P here, same like this. The distance between midpoint to the point P, always we need to find the distance between midpoint to the point P only. Let me consider it is X. Okay. Now, what is the potential at this point? What is the potential at this point? There are 2 potential we have. The potential at that point P with respect to negative charge and as well as positive charge. 2 we have to sum. This let me consider Q charge, this is Q charge. Very simple. So potential at point P is equals to sum of, let me consider this is charge 1 Q1, this is charge 2 Q2. Both are same only QQ only, but 1 and 2 we will consider. V1 plus V2 we can consider. What is V1 here? Negative charge. So how can you how can you take this KQ minus Q minus KQ by R? R means what is the total distance between point P and this? X plus A. Try to understand X plus A plus positive charge, that is KQ by X minus A. X minus A. Are you understanding? Now Vp is equals to, write down, KQ is the common factor, X plus A into X minus A, it is the denominator, it is the LCM, And first we will find x minus a. Try to understand. What is that? Yes, x minus a. For that minus we will be understanding. Make it as minus plus x plus a. In this way we need to understand. So now kq is a common factor. Now kq by x square minus a square, that is a common factor, into minus x plus a plus x plus a. In this way we need to. X will be cancelled. Then 2a will be getting. So what is the final formula will be getting? Vp is equal to, write down here. So 2a into kq divided by x square minus a square. This is what potential of the dipole, axial point, potential of the dipole on axial line. See, 2a into q, dipole moment. So finally you will be able to find get the answer as k into p, kp divided by x square minus a square. This is the final formula of the potential due to axial line of the dipole. Potential due to axial line of the dipole. So far we have discussed about electric field. Electric field is different, potential is different. Try to understand. Next we will go for short dipole. For short dipole, what is the potential? Vp is equals to, what do you mean by short dipole? X is very greater than a. This is the condition for short dipole, remember? In the case of electric field also same condition we are taking. So x is very greater than a means, less than a means, then a will become 0. Then what is the final answer? For short dipole, Vp is equals to kp by x square. It is important. So this is what about potential due to a dipole, potential on axial line of the dipole. Axial line. Next we will go for equatorial line. Equatorial line is very simple. Axial line is also simple only. It is not vector form. It is scalar only. So we are preparing for the negative positive charge. It should be very clear with that concept. Then we will go for potential due to dipole. A second part, that is equatorial line. Potential due to dipole on equatorial line. What do you mean by equatorial line? Negative charge we have to take first, positive charge we have to take next. See, exactly perpendicular bisector of the axial line is called as equatorial line, you know very well. The distance between here to here is a. Same, the distance between here to here also a. This you know very well. And take any point on the equatorial line. Let me consider point P I am taking here and join these two. Fine. See, if it is a, if it is x distance we are taking from the center of the dipole. And then after that, what is this? X square plus a square under root is the distance between P to the positive charge. And here also x square plus a square is the distance between P to the positive charge. Negative charge, positive charge, both. So once you know the values, then what we have to do here in this case? Try to understand. Now what we have to understand here, see, Vp is equals to, it is a scalar form. So superposition theorem. For this negative charge, minus kq, what is the distance? X square plus a square under root plus kq by x square plus a square under root. Fine. See, both are same now, it will become 0. So potential on any line of the equatorial line, any point on the equatorial line is 0. Actually, it is a three-dimensional figure. You will be getting the plane. So how it will be? Minus charge, positive charge, there will be a plane. Here all potential is 0 potential. So everywhere at any point you can consider on this three-dimensionally the potential is 0. This kind of plane is called as equipotential surfaces. Or equipotential surfaces we will say here. Are you understanding? This is what about the concept of equatorial line and axial line. See, at any point is very simple. Let me go for any point, potential at any point. Let me clear with that also, then you will go for the remaining topic. Okay, fine. Potential at any point. Potential at any point due to a dipole. First write down a dipole. Negative charge, positive charge. You know very well dipole in a sense, it has dipole moment P bar. P bar direction is this. Let me consider at any point means point P here. Now this is what equatorial line, this is what axial line, this is P. Okay, fine. So let me draw a position vector for this. It will become P cos theta and perpendicular one become P sin theta. You know this because in the derivation, general derivation also we have done this. If it is theta angle, P cos theta, P sin theta. Let me consider this is a point here where we have to find the potential Vp. So P, it is a P. Vp is equals to, see, this is the distance x we need to find. In this case, x is very less than a, we need to understand. Only for short dipole we have to say. This short dipole concept we need to use here. This is the condition. X is very less than a. Now in that case, what will be happens here? Vp is equals to, what happens? Vp is equals to, so first thing is P cos theta. So Kp cos theta by x square. This is the axial plus equatorial is 0. Equatorial is 0 already we know. Equatorial, on equatorial plane 0 is the potential. So finally we will be getting Vp is equals to Kp cos theta by x square. This is very important formula. This is at any point P, at any point which has the distance x, at the distance x, then the formula for this is Kp cos theta by x square. Try to understand. Kp cos theta by x square is the formula. So Vp in a sense, what is Vp here? Potential at point P at any point. Condition is